Yes. Hello.
I just want to ask, we don't have attendance for today.
No, attendance for today then. Okay. Let us proceed with the lecture 20,
Okay,
which is on this Chebyshev filters. Right. So this is continuation from our lecture 19, which was focusing on Butterworth filter. Yeah. So basically, as I mentioned in our lecture 19 before, for this filter design, we're going to have a look at two types of filter. Yeah, the first one is Butterworth, which has been learned in lecture 19. And for this lecture 20, we're going to have a look at the second type, which is a Chebyshev filters. Yeah. This will be the I can say the theoretical part, yeah, the fundamental part of Chebyshev filters, which is if we can compare this, yeah, with the Butterworth filter that we have done last time. Okay, so the Chebyshev filter basically is derived from Chebyshev polynomial, yeah? Right? So it's Chebyshev polynomial, which is after this name after this mathematician from Russia, Mr. Pavlovich Chebyshev. Okay, so if we compare the frequency response, yeah, of the Chebyshev filters and the Butterworth filter, we can say that for these Chebyshev filters, we can have a ripple. Yeah, we can have a ripple in the pass band. Yeah, comparable to a Butterworth filter. Yeah, if we can have a comparison with Butterworth filter last time. For the case of Butterworth filter, the pass band is said to have a straight line. Yeah, straight line. Okay, which is said to be in terms of comparison. Yeah, in terms of comparison, I think for the Butterworth is better as compared to Chebyshev. Because if you have the ripple for the pass band, it means that you're going to have more noise. Yeah, we're going to have more noise. Yeah, for the case of Chebyshev filters as compared to the Butterworth filter. Okay, yeah, that should be the first comparison. The second comparison is that the roll off, yeah, the roll off from the pass band to the stop band. For the case of Chebyshev, it is more steep. Yeah, it's more steep as compared to the Butterworth that we have done last time. That is less steep as compared to this. Yeah. So in terms of frequency selection or cutting off the frequencies, the Chebyshev filters is better. Yeah, Chebyshev filter is better as compared to Butterworth in terms of frequency selection. Okay, so that should be two comparison that we can have for the case of Chebyshev and Butterworth filters. Yeah, so for the Chebyshev filters, we have two types, but our concern will be only on the first type, yeah, of Chebyshev filters. Okay, so as what we have learned last time, in the case of Butterworth, we are going to design, yeah, going to design the filters based on the given specification, yeah. But before we can design it, we need to understand few theoretical issues related to Chebyshev, yeah. Right. So in order for us to calculate the filter order, yeah, we need to understand, yeah, what is the theoretical issues, what are the equations, yeah, related to these Chebyshev filters. Okay, so for the case of n order of low pass Chebyshev filter, so I'm going to use a low pass, yeah, low pass as my reference, yeah, because the same thing that we did for the case of Butterworth last time, where we use low pass filter as a reference, yeah. So the high pass filters can be obtained by using transformation table, yeah, transformation table. We're going to show you after this, yeah. Okay, so for the case of Chebyshev, this is the transfer function or method response of transfer function in terms of the magnitude. So the h n j omega and refer to the n order. It can be written as 1 over square root of 1 plus epsilon. Epsilon is a ripple factor, yeah, ripple factor, because we have understand from the previous slide that for the case of Chebyshev, we have a ripple, yeah, for the case of passband. So the ripple factor is written to be epsilon, okay. And Tn here is the Chebyshev polynomial. Okay, going to see after this what is Chebyshev polynomial, and the omega p is your passband frequencies. So this is the equation that govern, that govern the Chebyshev filters. Yeah, this is the equation of the magnetic response. Right. Again, I just want to remind you that you don't have to memorize all of this. Yeah, you'll be given this equation. Right. So let's have a look at this slide. So this is the typical low pass filter response of Chebyshev. Yeah. So if we can have a look here, we have a separation between a pass band and a stop band. Okay, so the pass band is the part where we have a ripple, and the magnitude of the ripple is noted as a max. Yeah, so that should be the amplitude difference, of the ripple. Okay, and we have the transition band between the pass band and the stop band, and we are going to have the omega p, which is the pass band frequency range, and we have the stop band frequencies there. Yeah. Right. So it is known based on the theoretical understanding of the Chebyshev polynomial that the Tn will be alternated between 0 and 1. Yeah, so this is the numerical value for the Chebyshev polynomial Tn. And hence, we can write that if the Tn is said to be alternated between 0 and 1, yeah, if we base on this slide, yeah, from equation number 1, the Tn will be having the minimum value of 0 and the maximum value of 1. Okay, so if we have Tn equal to 0, as a result, we're going to have the amplitude j omega shall be equals to 1. Okay, and if we have Tn equals to 1, yeah, in which for this particular case, we assume that your omega should be then equals to omega p. Okay, okay, and we're going to have that the value for your, let me check, yeah, so the value for your hj omega, the amplitude for this hj omega, okay, shall be equals to 1 over set of 1 plus epsilon squared. Okay, so that should be the case, yeah, so that should be the case. The value for the magnitude response of the Chebyshev filters, the maximum will be equals to 1, and the minimum will be equals to 1 plus 1 over 1 over set 1 plus epsilon squared. Okay, so means that these two values will be used to calculate the value of A max, because we can see that what we're going to have here, the maximum ripple, the maximum value of the ripple here will be the maximum amplitude of Hj omega, whereas the minimum ripple here will be the amplitude of this. Okay, so if I can label, that should be the amplitude maximum, and that should be the minimum amplitude. Yeah, so that the A max will be a difference between the maximum and the minimum, and as such, we're going to have this as the ripple amplitude. Yeah, which is the difference between the maximum amplitude and the minimum amplitude of the ripple. Okay, so we're going to have here that the amplitude for the ripple shall be given by this equation here, 1 minus 1 over set 1 plus epsilon squared. Okay, so for this, if you base on the equations, then the values in terms of dB can be written as 20 log, yeah, 20 log 1 minus 1 over epsilon 1 plus, sorry, 1 over set 1 plus epsilon squared. Yeah, we refer to this, yeah. So this is in linear scale. So in dB, that should be 20 log of A. Yeah, so 20 log of A will give us 20 log of 1 minus 1 over set of these values down there. And as a result, we're going to have 10 log of 1 plus epsilon squared. Yeah, so this is equation number 2 that enable us to find what should be the value of the ripple amplitude of A max. Okay then, so this is what happened in your passband region, yeah, for the case of low pass Chebyshev filters. And for the case of a stop band region, it can be written that the stop band attenuation alpha s yeah, which is again, the equations here is obtained from the equation number 1, yeah? We are referring to equation number 1, right? In which we just substitute the value of omega to be omega s, and the value of the amplitude to be equals to alpha s, yeah? So I repeat again, this equation is obtained from equation number 1 that we have seen earlier. So by substituting the omega of omega s, then you're going to get that the alpha s, which is the stop band gain, yeah, shall be equals to this equation. And as a result, we're going to have equation number 3. Okay, so that should be the equation of the Chebyshev filters for the stop band region. Yeah, so this is the equation in the pass band. This is the equation in the stop band. And the equation for the Chebyshev polynomial, the Tn is given by this equation here, equation number 4. Okay, so this is based on the theories invented by Mr. Pavlovich Chebyshev. So you don't have to memorize this. This is based on his theoretical understanding. Yeah. Okay then. So from equation number 2 that we have seen just now, this equation, we can write the epsilon in terms of A max. So we have this equation number 5. Okay. This is from equation number 2. And as a result, we can combine equation 3, equation 4, and equation 5, and we can find the filter order n of the low-pass Chebyshev filters, which is given by equation number 6 here. Okay, so this is how you obtain the filter order n of the low-pass Chebyshev filters, in which it will be based on the parameters of A max. This is based on equation number 2, parameter of alpha s, which is based on equation number 3. Then you have to know what is your omega Sn, in which I did mention here that omega Sn, for low pass filter, it should be omega s over omega p, whereas for the high pass filter, it should be omega p divided by omega s. Okay, so this is same like what we did in lecture 19 on the Butterworth filter. So we're going to use the same transformation for the omega Sn. Yeah, so you can refer to table F1 if I can refer to this table here. Yeah, this is the attachment that you're supposed to have in your Google Classroom. Okay, so the first picture is for Chebyshev parameters, all the equations related to Chebyshev filters. So what I meant just now is this table number F1, yeah, table F1. So omega Sn for the case of low pass filter, it should be this. For the case of high pass filter, it should be the other way around, which is omega p divided by omega s. Yeah, so that should be the substitution for the normalized stop band angular frequency omega Sn here. Right. So for our case here, since we are referring to low pass filter, so our omega Sn shall be omega s divided by omega p. Yeah. Yeah, so that should be the case lah, omega s divided by omega p lah. Okay, so further on, the 3 dB cutoff frequencies, it can be written as this. Yeah, so we can adopt these omega c values, and we can have it in this table, I believe. Yeah, so this is the equation for the omega c is here, right? It's given here, right? Omega c term, sorry. Yeah, omega c terms is here, is given. In which, sorry for that. Okay, so we have this equation here to calculate the omega c. Yeah, so we have it in this equation number 7 down here. Yeah. Okay, so this equation will be used in calculating the cutoff frequency omega c, where it need this information of passband frequency omega p, the filter order n, and also the ripple factors of epsilon. Okay, epsilon can be calculated based on equation 5. Yeah. Yeah. Number 5, equation number 5 is used to calculate the epsilon value. N is obtained from equation 6, and omega p shall be given in the questions. Yeah. Okay then. Okay, and then as what we have learned, remember that we have learned in lecture 19 on Butterworth filters, you need to calculate the N. Okay, That number one. Number two, we need to calculate the filter transfer function, right? You need to the HN, sorry, the HS, sorry, the HS. So that should be the design that you have to do for the case of the Butterworth filter. So the same things applied for the case of Chebyshev filters, in which you also need to obtain the transfer function for the Chebyshev filters. Okay, so first case, first thing first, you need to calculate the normalized transfer function. Yeah, same like what we did last time for the case of Butterworth filter. Okay, in which for the case of Chebyshev filters, the normalized transfer function is given by equation 8, yeah, in which H and S is Kn over the Chebyshev polynomial. Okay, and Chebyshev polynomial is given in table F4. Okay, I'm going to show you after this. Yeah, and one more thing from the equation number 8 is that we are having the Kn here. Okay, this Kn as your numerator. Yeah, numerator. Kn is a constant which is determined by the value of A max and the filter order n. Okay, so in case if you calculate the filter order n based on equation 6, yeah, based on equation 6 just now, this equation, yeah, number 6, you manage to find the n value. If your filter order n is odd, yeah, it's odd, so you can just take the Kn as equals to A naught. What is A naught? A naught is the value from the Chebyshev polynomial. We're going to show you after this. And if your n is even, so your Kn shall be based on this equation here, which is A naught over 10 to the power A max over 20. Okay, yeah. So let us have a look at the table here. Okay, so this is the equation for the normalized transfer function for the Chebyshev filters, the H and S, and we have the Kn here. Okay, let's have a look at the table F4. Okay, table F4 is here, which is the coefficients of Chebyshev filters. So what we have here is the coefficient for the Chebyshev filters for 4 cases of A max, which are 0.5, 1, 2, and 3 dB respectively. Okay, so what we have here, the first column here is for the A max. Yeah, A max of 0.5 dB. Here is A max of 1 dB. Okay, the third is the A max of 2 dB. And the third is the column for A max of 3 dB. Okay, so we have 4 distinct values of A max and 4 distinct values of Chebyshev coefficients. Okay, for instance, if in your problems, let's say you are given that the A max, you need to design a Chebyshev filters for the case of A max of 0.5 dB. And by applying equation 6 just now, which is which is to calculate the filter order n, and if you manage to get that the filter order n is equals to 4, for instance, so your A naught is this one, which is 0.3790. So these are the filter order, I mean the Chebyshev polynomial for the case of n equals to 4, yeah? The A naught, A1, A2, and A3. Okay, so we are given only 4 values of A max, yeah? 0.5 dB, 1 dB, 2 dB, and 3 dB only. Okay then. Okay, so let's proceed with the next slide then. Okay, so now these are the steps that will be required in the design method of low pass Chebyshev filters, which is on the transfer function values. Yeah, number one, you have to obtain the filter order n using equation 6. Right, so if your n calculated is 2.4, so straight away you just choose n of 3, and the same things applied. Let's say here I put n is 3.01, so you should be rounding up further to 4. So that should be the technique how you obtain the filter order n. So the same things applied, I believe, for the case of a Butterworth filter that we have seen previously. Okay then. So that's the first step, which is to calculate the filter order n. Number two is to calculate normalized transfer function. Normalized transfer function, the HNS. So we have seen just now, HNS. So HNS shall be based on two values, which are the A max. A max is based by right is a predetermined value. Okay, it should be given. Okay, and then we have based on the filter order of n, which is calculated from the first step just now. Okay, so once we have the n, whether it's even and odd, you can determine what should be the kn, because kn, which is the constant of your normalized transfer function, if you base on the previous slide here, the kn is to be based on the odd or even values of your order. Okay. Right, so this is the table F4 that I did mention just now. Okay, so that should be based on calculating the Kn. Okay then, so that should be second step, which is calculating the normalized transfer function. So finally, you need to calculate the actual transfer function, which is the HS. So the HS can be calculated based on the obtained HNS just now, which is based on this transformation table F5. So we have a look, we have come across this table F5 previously when we learned about the Butterworth filter. Okay, so our concern for the case of Chebyshev should be outside the column here, outside the column here, because the column is for the Butterworth. So outside here is for the Butterworth, is for Chebyshev. Okay, so for the case of a low pass filter, for the Butterworth, it is S over omega C. Okay, S over omega C, but for the case of Chebyshev, simply it is S over omega P. Okay, and again, for the high pass filter, for the case of Butterworth, it is omega C over S, but for the case of Chebyshev, it is omega P divided by S. Okay, so I put example here. If we have a low pass Chebyshev filters, this is normalized transfer function, HNS. So the actual transfer function simply can be obtained by substituting or by transforming all the S into S over omega P. Okay, so that will give us the actual transfer function for the low pass Chebyshev filters in this example. Okay, so that should be three steps that need to be taken in obtaining the transfer function of Chebyshev filters based on the given specification. Number one, calculating the order based on equation 6. Number two, obtain normalized transfer function, in which you need to obtain the n, then only you can find the kn. Okay, and finally, you need to find the actual transfer function based on the transformation in table F5. Okay, that should be three steps that need to be taken in Chebyshev filter design of a transfer function. Right, hopefully you understand about these design techniques of Chebyshev filters. Okay, let's have a look at this example. We need to design a transfer function of a low pass Chebyshev filters that having these parameters, this specification. Number one, we are given that the A max is less than or equals to 3 dB. So it means that our A max is 3 dB, given the question is 3 dB. The passband region is from 0 to 12. So here we have omega P equals to 12 radian per second. Okay, and for the case of stop band region, the specific given is that the alpha S is negative 23 dB and your omega S is 18. Omega S is 18. That should be your stop band frequencies. Okay, so basically these are the conditions, the parameters given in your specification. Okay, so as usual, because you need to design a transfer function, the first step that need to be done is that you need to calculate the filter order n is equal to 6. So by putting all the information, okay, in which if you base on equation 6 just now, you need to substitute, because you have for the case of low pass filter, omega Sn should be omega S over omega P. So we are supposed to substitute the values given in the question. And then another one is you are given the alpha S and also you are given the A max. Okay, so these are the four important parameters that need to be substituted in equation 6. Omega S, omega P, then you have alpha S and you have the A max. Okay, so by then you are supposed to get the value of n will be equals to 3.47, and as a result the round up value should be 4. That should be your filter order n. Yeah. Okay, so I suggest you to try to substitute all these values, these parameters in the equation 6, and you must be able to obtain this n of 3.47. Yeah. Okay, and then you need to use table F4 to find the H and S. So we know that n equals to 4 for the case of 3 dB. So let's have a look. So this F4, so 3 dB, it is for this column. And you have to choose for the n equals to 4. So you're going to have these 4 coefficients of Chebyshev polynomial starting from A3, A2, A1, and A0. Yeah, right. So based on this, you can then substitute them in this particular Kn, yeah, because we know that since n is even, so your Kn is based on this equation or this terms, which is A naught over 10 of A max over 20. So based on table F4, you manage to get that the A naught is 0.1769. So you're going to substitute it here. A max is 3 dB. So 3 divided by 20. So 10 to the power of 3 over 20 will give us 1.4125. So end up the value for Kn will be 0.1252. So that should be your Kn, yeah? Okay, so for this, you can find that you can write that your H and S supposedly shall be equals to Kn, which is 0.1252 divided by S to power of 4 plus A3. Okay, I just use A3, yeah? S power of 3 plus A2, S power of 2 plus A1 to power of S, A1 times S plus A naught. So that should be your normalized transfer function, yeah, in which A3, A2, A1, and A0 shall be based on these obtained values, yeah. Okay then. Okay, so that's your normalized transfer function. So finally, you're going to get this, yeah. That's what we have done just now, H and S. So for the actual transfer function, because we are dealing with a low pass filter, so it should be a transformation of these S terms here to be S over omega P. So end up your actual transfer function shall be based on these equations here. Okay then, yeah. Any question for this example number 1? No, yeah? Okay, so let us have a look at this example number 2. Okay, so again, we have to design a transfer function for low-pass Chebyshev filters with the given specification. For this first information for the passband region, the A max is 2 dB. The passband region is between 0 and 10, so your omega P is 10. Okay, and for the case of stopband region, the alpha S is negative 20 dB, and your stopband frequency is 16.5 dB. Sorry, not dB, yeah, it's radian per second. My mistake then. 16.5 radian per second. Okay, so using these 4 important parameters, A max, omega P, alpha S, and omega S, you can obtain the N, the filter order, in which the N is 2.99, and round it up, you're going to have 3 as the filter order. Okay, and by calculating by using the table F4 to find out the Chebyshev polynomial. Okay, so since we have A max of 2, yeah, so you need to base on this third column there, and of 2, A max of 2 dB. So your N just now equals to 3, so we need to be based on these coefficients, A naught of 0.3268, A1 of 1.0221, A2 of 0.7378. So that's why we have the value here for respective Chebyshev coefficients, yeah? Okay, and again, since the N is odd, which is 3, so your Kn simply replace as A naught, which is 0.3268. Okay, so that should be your Kn, yeah, because previously, for the previous example, your N is even, so the Kn is based on terms of a naught over 10 to the power of mx over 20. But for this particular example, since n is odd, which is 3, so simply we just substitute the kn to be a naught, which is 0.3268. So then we are supposed to get the h and s to be equals to this, yeah, based on the kn and the Chebyshev polynomial. Okay, and finally, you can obtain the actual transfer function simply by just substitute all the s or transform all the s in this equation or in this normalized transfer function to be s over omega p. Yeah, since our omega p just now is 10, so you have to calculate, you have to transform all the s term to be s over 10. So that should be the actual transfer function for the Chebyshev filters with the given specification. Okay. Okay, so that's all for our syllabus, yeah, for this course. Okay, any questions for this lecture number 20? No? Okay, so if there's no question, I think we can now have a discussion for your final examination format. Yeah, so let's have a look at your final examination format. Let me add something here. Sorry for that.